we will move on to a new topic, which is shear stress distribution in thin walled beam cross section due to applied shear load. So, in all this while, in the last week we have discussed pure bending of a thin wall cross section beam. So, for pure bending, the only stress that developed was the direct stress or normal stress, which is sigma z, z being the lengthwise axis of the beam. So, what we discussed about is if we have a beam with arbitrary boundary condition. For this case, I am just showing a cantilever beam with fixed free boundary condition. So, the problem that we were discussing had a pure bending problem, that is, it was either only mx or my or both of them. So, the only load that acted on the beam were pure bending moment. The bending moment was due to pure moments applied on the beam. Now, bending moment can also be applied through forces, through shear forces. So, if I apply so instead of applying pure, so this is the case of pure bending. Now, if I take the same beam and I, instead of applying pure bending moment on the beam, if I apply this is z, this is x and this is y. If I apply a shear force, say F x or S x, if I apply a shear force S y and S x, so this is shear forces S x and S y. Now, for this case also bending moment would be produced. So, bending moment would be given as S x into, so m x in this case is going to be S y into L minus z, whereas m y is going to be S x into L minus z. So, in the second case, so this is case 1 and this is case 2. So, in the first case, the only external thing acting on the beam are pure bending moment m x and m y. So, pure bending moment m x and m y. So, but in the next case, the applied moment are shear force, applied excitations are the shear force S x and S y. So, S x and S y in turn will produce bending moment m x and m y, but this is not pure bending, because here apart from, so this is not pure bending, because in case 2 apart from the bending moment m x and m y, there will be also shear forces acting on the beam on any arbitrary beam cross section. Now, in case 1, the only non-zero stress is going to be normal stress or direct stress. Whereas, here the non-zero stresses are both normal stress and shear stress. So, in this week, so now out of this normal stress and shear stress that will develop in the beam cross section due to applied shear force, we know how to handle normal stress. We know how to find out the normal stresses in the beam cross section, because from Sx and Sy we will know Mx and My, and we will apply that Mx and My and get the normal stresses using the expression that we have derived in the last week's lecture. What we do not know is how to find out the shear stresses. So, in this week, this is the problem that we are going to deal with. So, we are going to find the shear stresses in a thin wall beam cross section due to applied shear forces Sx and Sy. So, this is the problem statement that we are going to do in this particular week. Now, first let us find out how to obtain the shear stresses in a thin wall beam cross section. So, this shows a thin wall beam the cross section. So, the cross section is a thin wall C cross section. Okay. The x, y and z axis are the same as we have considered earlier. Z is the lengthwise axis of the beam, x and y are the cross sectional axis of the beam. Now, let us consider a small elemental portion of the beam. So, let me take a small elemental portion which is, so the beam, let us consider that beam has a thickness T. So, thickness of the beam is T. Now, if we take a small elemental portion and draw that elemental portion and try to see what are the stresses acting on the elemental portion. So, this is ds, this is dz, and this thickness is T. Now, let us try to find out the stresses that are going to act. So, this is the elemental portion, of the beam. Now, let us make certain assumptions before we proceed and find out the stresses that are acting on the elemental portion of the beam. So, let me just erase this off and just let us try to find out the assumptions that we are going to make, to which the assumptions will be simple, but those assumptions will make the calculations and derivation much more simple. So, let us try to find that out. So, the assumptions involved, these assumptions are mostly based on the idea or on the information that the cross section is thin walled. So, the first assumption is that that there is no axial constraint on the beam. So, the cross section of the beam has no axial constraint, that is, it is free to deform in the out of plane direction. So, it is free to deform in the z direction. So, the deformation in the z direction is not constrained. So, axial constraint effects are neglected. We are not considering any constraint in the axial direction. The second assumption is that the shear stresses which are normal to the beam surfaces. So, this shear stresses, this shear stresses. This shear stresses, the ones that are normal to the beam surfaces are considered to be 0. So, shear stresses we need not call it 0, we can call this that they are neglected. And why this is a fair assumption? It is a fair assumption because the outer surface of the beam, that is this surfaces of the beam, the outer and inner surfaces of the beam are stress free. So, since these are stress free, since the out of plane shear, the normal shear stresses are 0 at these surfaces, and since the thickness of this, the wall thicknesses are very small and they can be neglected. So, let me try to reframe what I said in other words. So, the normal stresses, as I have shown, the shear stresses, sorry, not normal stresses, they are shear stresses. The shear stresses which are normal to the beam surfaces are assumed to be 0. Why this is a good assumption? Because the outer surfaces of the beam, outer beam surfaces are stress free, and since the thickness of the beam wall is very small and the two ends are 0. So, it is a small magnitude stress in the shear stress in the normal direction, which is very small and can be neglected. So, we can say that since they are 0 at each surfaces, and the wall thickness is small. Now, the third assumption is that the direct and the shear stresses, or the normal and the shear stresses, are considered constant across the thickness of the cross section. So, the normal or direct and shear stresses are assumed to be constant are considered constant across the thickness. So, across this thickness, okay, though ideally the direct stress or normal stress and the shear stress are varying, but we can very well assume them to be constant because the wall thickness is very small. So, even if there is a variation, the variation is too small to be considered and they can be very well considered to be constant. So, these are the three main assumptions that we make while deriving the expression for shear stress in a thin wall beam cross section due to applied shear load. Now, once we have understood these assumptions, let us try to write down the stresses that are acting on this elemental portion. So, one is sigma z. So, here I will have sigma z plus so this is one component of the stress that we have. This is the normal stress that we have, because the shear forces are going to produce moment and the bending moments are going to produce direct stress, and the direct stress is going to vary along the lengthwise direction of the beam, because the moments are also varying. So, it is not a pure moment, it is a moment due to shear force, and therefore, the moments are varying along the length of the beam, and so sigma z is going to vary along the length of the beam. So, that is why for this elemental portion we have written this increment in the normal stress. Now, let us see what are the shear stresses acting on it. So, the shear stress on this direction is tau s z, and on this direction we have the increment of that, which is tau s z plus del tau s z by del s into ds. Similarly, we have tau s z here, and on the opposite direction we have tau s z plus del tau s z by del z into dz. So, these are the stresses that are acting on an elemental portion. There should have been a stress in this direction as well, but as we have discussed while in the assumption that these stresses are neglected. So, these are the only stresses that are going to act. So, one component of the shear stress in each of the plane is neglected. So, this is the only stress that we have considered. Now, let us notice one more thing, that the one dimension of the elemental portion is taken as ds, because we do not take it as dx or dy, because it cannot be dx or dy throughout, because ds can be ds is dx when it is on the top and bottom flanges, whereas if we consider an element here, my ds is going to be dy. So, therefore, since whether it is dx or dy is not constant, we are taking it to be ds, where s could be anything of either dx or dy. Now, with this stresses, let us try to write down the force balance equation. So, let me write down the force balance in z direction. So, if we write down the force balance in z direction, let us see what we have. The first thing we have is sigma z now the area of this cross section. So, the area of this cross section, the area of this cross section is ds into t. Right. So, now sorry ds into t minus we have sigma z from the opposite direction, which will be again ds into t. Now, the other force in z direction is going to be tau s z plus plus the area of this portion, plus the area of this portion. So, which is going to be dz into t, and then we have to negate tau s z into t into dz. So, and that because for equilibrium of the elemental portion has to go to 0. Now, let us simplify this expression. So, this and this cancels out, this and this cancels out. So, what we have from this expression is del sigma z by del z into t dz into ds plus okay. So, this is the expression that we have. Now, we can also eliminate this portion and further simplify the expression to del sigma z by del z into t plus del tau s z by del s into t, that is equal to 0. Now, why I have left t and I have not eliminated t? Because t into tau s z can be written as q, and we know that neither tau s z is constant, neither t is always constant, but this product of tau s z and t, which is the shear flow, is constant in a portion if there is no junction at any point. So, at any portion between two junction, the shear flow is constant, and therefore, instead of writing tau s z in the equation, we replace the product of tau s z and t as q. So, therefore, this expression can be written as del sigma z by del z into t plus del q by del s is equal to 0. So, this expression is an important expression and will be used further to derive the expression of the shear stress. So, from this expression, let us see how we can derive the shear stress. So, we have del sigma z by del z into t plus del q by del s is equal to 0. So, this is my equation 1. Now, let us see what we can do to this expression. Now, we know that sigma z from our previous week's lecture, that sigma z is nothing but my Now, from this expression I can actually find out T into del sigma z, or let us forget about T and just let us find out del sigma z by del z. So, what is that going to be? That is del m y Now, let us, so what I have done is that I have taken the derivative with respect to z in both the both sides of the above equation. Now, let us see what does this imply. What does this imply? So, we know from our basic solid mechanics that the derivative of m, that is dm by dx, is going to be the shear force. We know that from our basic equations of solid mechanics. So, therefore, this is basically my Sx, this is Sy, this is again Sy, and this is Sx. Therefore, del sigma z by del z into T can actually be written as Sx Ixx minus Sy into Tx plus Sy Now, from equation 1, we get that del q by del s plus T del sigma z by del z is equal to 0, or we can say that del q by del s is basically minus T del sigma z by del z. So, therefore, del q by del s can be written as Sx Ixx minus Sy Ixy by Ixx So, let me call this as equation 2. Now, we have got the expression of q, the derivative of q in terms of the applied shear forces Sx and Sy, the sectional property Ixx, Iyy and Ixy, and the coordinate of a given point on the cross section, that is x and y, and the thickness T. Now, this expression can be used to further obtain the value of q, which will be taken up in the next lecture. Thank you.